Hello everyone, and welcome to video lecture for Chapter 3, Steel and Other Metals, Welding Principles and Practices book. This is a very long chapter. This is almost 100 pages in the book, or more, I forget. It's going to be a several hour lecture. I'm going to try to break this up into different sections. I'm going to be doing a lot of highlighted and bulleted items out of this chapter because there is so much material to cover that I want you to highlight, circle, and then you can come back along with the PowerPoint presentation and be able to restudy and research the things that I feel are important. Okay? So let's start out. The objectives. We're going to talk about the steel making processes, metalworking processes, internal structures of steels, name various alloying elements, their effects, various types of ferrous and non-ferrous metals, their applications, and so forth. This is a brief overview of welding metallurgy and a baseline of metallurgy. Okay? We can get far more advanced in this material than what we're going to cover in this one chapter by far. This is a baseline to start understanding, and it helps you understand grain structures and why preheating and post-heating, and to get you thinking about the welding and machining processes and how to work with those types of materials. Okay, again, we can get a lot more in depth. We can break it down. We can go into crack tip, opening displacement, all sorts of other stuff with it. I'm trying to keep it a broad overview that I feel is just general knowledge for the welder and would helps out tremendously. I can't tell you how many welders I've worked with that have been welding for 30 years. Some of them knew a lot of this stuff because they go on their own and start reading about it. But the majority of them had never been through any formal training or even understood the differences between grain structures, why we need to preheat and post-heat certain steels, why we have to be careful of certain things, walking away from them, letting them cool down, and so forth. Okay, this is a really good chapter. It just kind of helps start in the whole process of beginning to prep your metal, purchasing steel, and so forth. Okay, all right, so let's get into it more in depth. First things first. There's going to be quite a bit of this video. I might not be in front of the camera. I am just going to be here to the side of it, reading, talking about bulleted items. So first page in this chapter is page 34, Steel and Other Metals. So I want you to go over first paragraph down, last sentence in that paragraph. Metals are separated into two major groups, ferrous and non-ferrous. Okay? Highlight that, bullet on it. There's also a bullet under ferrous metals. We should know what ferrous metals are. Let's read the definition from the book. Ferrous metals are those metals that have a high iron content. They can include the many types of steel and its alloys, cast iron, and wrought iron. Non-ferrous metals are those metals that are almost free of iron. The non-ferrous group includes such common metals as copper, lead, zinc, titanium, aluminum, nickel, tungsten, magnesium, brass, and bronze. The precious metals, gold, platinum, and silver, and radioactive metals such as uranium and radium are also non-ferrous. Okay, I want to back up to that non-ferrous. You notice this section here. It says almost free of iron. So if it's considered a non-ferrous material, doesn't mean that it has zero iron in it. It just means that there's a very, very low percentage as well. Okay? Some people start talking about ferrous or non-ferrous. So for example, a stainless steel material can be considered a non-ferrous. It is steel. It just has to have chromium content. There are certain parts of it that do have iron in it. Ferritic types of stainless steel and so forth as well. Okay. Not all steels, when you get into the non-ferrous, it can be different. It can be rather confusing to start out with. so we can start researching it, going forth with it, but we're just going to stick to here, okay? Non-ferrous metals common: copper, lead, zinc, titanium, aluminum, nickel, tungsten, magnesium, brass, and bronze. Precious are the gold, platinum, and silver. Radioactive are uranium and radium. Okay, let's go to the book. Underneath steel, I would highlight this chapter. I'm going to read the first two bulleted items. Steel is a combination of iron and carbon. So steel is already an alloy. Okay? First things, it's not a pure element itself. It's an alloy product. Iron and carbon. Okay? The percentage of carbon determines how strong and hard the steel is. Real quick, the higher the carbon content, the higher the strength goes. Okay? They're directly proportional. Go down to the very bottom, the last sentence in that chapter, page 34, left-hand column. Starts out, well, let me back you up. About halfway through the paragraph, it starts out, up to a certain point, the more carbon steel contains, the stronger and harder the steel will be, but will have less ductility and a more cracked, sensitive microstructure. Although it's possible to weld nearly all the ferrous and non-ferrous metals and alloys, this chapter will be concerned primarily with steels in the low and medium carbon ranges. These are the steels that the student will be primarily concerned with in the practice of welding. It has been estimated that nearly 80% of all weldments are fabricated from steel. 85% of the total amount of steel welded is in the mild, low-carbon steel classification. So you see it on the PowerPoint. Might be something to keep in mind. So we're on page 35 under the history of steel. First paragraph, you can read through it. The Assyrians, 3700 before Christ, first recorded use of iron. Low carbon iron first produced in low flat hearth furnaces. Okay? 1350 BC to 1300 AD, all iron tools and weapons produced directly from iron ore. Okay? So there wasn't a lot of application of carbon built into this. Okay? Now, around this time, it's actually before this time, during like the Viking era, they started figuring out that there's some stuff that you could add to it to gain some properties. If you get a chance, there's a show out there called The Making of the Viking Sword. It's a PBS special. You can look it up online, and I believe you can watch it through, I'm trying to think of the website, but if you look up the Viking Sword, it's a PBS video. They talk about building an Ulfberht sword, which was one of the swords during the Viking era, and he regenerates it in the old-fashioned way, modern day, but he goes back to doing it out of air bellows and an old furnace and clay, and he's got a few modern technologies in there, but you know, for example, he uses glass and so forth to help pull the flux out, which they probably didn't have a lot of glass at the time. But it's really an interesting show to kind of start to watch. You know, it's a family-friendly show as well, just to think about the history. They talk about metallurgy, the structure within it, and I might even try to see if we can get it here and put it in, but it's a couple-hour video. But a really interesting watch and very informative, in my opinion. Furnaces increased in height and charge, and then we get into the modern blast furnaces. Okay, let's go back to the book. Left-hand column, page 35, second paragraph below, history of steel. The very end of that paragraph, the sentence starts out, the modern blast furnace is a shaft furnace. Okay? And I don't know if this has pictures or not. We will get into that. I'll try to remember when we get there. You can see it on page 39. There is a modern blast furnace on the right-hand page. You can look through, see how it parts gradually come down to each other in a shaft type of setup, so forth. Okay. Little known of the first process for making steel. Tools found dating back to 1000 to 500 BC. Remember, we talked about the history of welding. A lot of the original steels and materials were made out of brass, bronze, so forth, before the steel process come in. Prior to the Bessemer process, two methods were used: the cementation and the crucible process. Okay, cementation process is where increased carbon content by heating iron in contact with hot carbon in the absence of air. Still used to a limited extent. The crucible process means it's melting the iron in crucibles in which carbon's already added. And it's replaced by various electric furnace processes. So real quick, increased carbon content by heating iron in contact with hot carbon in absence of air. So this is the first one. If you go to watch that Viking sword, it's very similar to what they're doing is they got charcoal there, okay? Charcoal or coal, coke, whatever that they're using, and that product is being very, very hot and it's producing carbon. So the material, the metal, is laying on it, and it's absorbing that carbon as it's being put in there. Now this is strictly talking about the absence of air, so in a vacuum chamber. However, very similar to being buried into a pit full of coal. Okay, most of the air at that point has been consumed, so there is a lack of air within the coals, and the carbon is drawn into the steel to add strength to it. The crucible process means that you're melting it and drawing it out as you're adding carbon to it. So it's kind of in a liquid form, so to say. One way to help keep these two separated. Okay? Let's go to page 35, left-hand column. 2 paragraphs from the bottom. It says, during the Middle Ages, both the cementation processes, or cementation and crucible processes were lost to civilization. The cementation process was revived in Belgium about the year AD 1600, while the crucible process was rediscovered in England in 1742. The crucible process eventually came to be used chiefly for making special steels. The cementation process was highly developed and was also used extensively in England during the 18th and 19th centuries. This process is still used to a limited extent. The crucible process has been replaced by the various electric furnace processes for making special alloy steels and carbon tool steels. Okay? Steel making in the U.S. Page 35, right-hand column. Second paragraph down. Very little steel was manufactured in America during the early days. The first patent was issued in Connecticut in 1728. A succession of events spurred the growth of the steel industry. And you see all those bullet items, which are also here on your PowerPoint. Make sure you understand these. I would put a bullet next to them. Okay. Next paragraph. Currently, the largest steel producer in the world is China at 500.5 metric tons. The European Union is second with 198 metric tons, followed by Japan with 118 metric tons, and the U.S. with 91.4 metric tons. I would be curious to see what the modern day statistics are. I believe now we are up there quite a bit more than we used to be. Maybe when we take our first break from lecture, we will come back. I can try to find that info real quick, okay? All right. Changes in U.S. steel production. The reduction in number of blast furnaces. Well, let me back up here. I do know this, and I'll find the statistics. But 70% Over 70% of the steel made in the U.S. Every year is recycled. It's the most recycled material of any material we use, more than wood, more than paper, more than plastic. I mean, tremendously more as well. Not exact figures, but just a comparison. Okay, say 100 million tons of steel are recycled a year. I believe it was close to about 1 million tons of steel or tons of plastic is recycled in a year. So just a quick comparison, it's drastically much more than anything else that's recycled. Part of the reason it's better money, it's hard to get rid of, you can't just throw it away, you kind of have to take it somewhere. And I think we think of it as us as the consumer thinks of it as a highly recyclable material. And it can bring a little bit more money than other things. Not as much as aluminum, but definitely more than plastics and so forth, okay? All right, moving on. Reduction in number of blast furnaces is from 250 down to 36, and I bet there's even less than that today, modern day. I don't think there's very many steel-making facilities within the United States left anymore. Around 2008, 2009, there was a large buyout. Several companies. We have one here in Portland area. It was bought out by a company from Russia. He bought several steel-making facilities within the area, Portland, or within the country, I mean. I know he bought several within the Pittsburgh area. I have family in West Virginia that have worked and retired from U.S. steel mills and so forth. So I know that they've been purchased, bought up, and there's sometimes they're doing limited production, okay? There are no open hearth furnaces. It's increased the use to recycled steel. The perfection of welding processes to join metals, and also the coating and corrosion resistance too. You know, we have done, not just perfection of like the weld itself, but the technology that has come to light in the last 10 years of alloying elements that we're putting in filler metals to improve the characteristics of steel and welding processes, on top of the corrosion resistance and coating to minimize rust and protect the elements from salt water and so forth. The technology there has increased as well to where things are lasting longer than they used to. We are able to create, most of our architecture is larger openings, so we're not using as much steel to frame individual smaller cells or rooms, however you want to put it. We're using larger areas in our modern day architecture. Okay, raw materials. Let me back up to page 35. Okay. Right-hand column, third paragraph up, it starts out, the perfection of the welding process as a means of joining metals has speeded up and expanded the use of steel. The adaptability of steel to manufacturing processes and its ability to join with many other metals to give a wide variety of alloys have also contributed to its widespread use. With the continued development of gas tungsten arc welding, gas metal arc welding, flux core arc welding, laser beam cutting, plasma arc cutting, the welding and cutting of aluminum, stainless steel, titanium, and other alloys have become routine production applications. Okay, stops there. We'll go to page 36, underneath raw materials for the making of steel. I'm going to read from it, highlight this entire chapter and section, or not chapter, but this entire paragraph under raw materials for steel. Huge quantities of raw materials are needed to produce the vast amount of steel needed by humankind. The U.S. is well supplied with the basic resources such as iron ore, limestone, and coal. The principal supplies of magnesium, or manganese, tin, nickel, and chromium necessary to the making of steel, and its always are found in other countries. We'll talk about the vast differences from coal to now electric induction furnaces here in a few, okay? As stated earlier, Continuing reading on. As stated earlier, iron occurs in nature in the form of compounds with oxygen. In order to obtain the iron, the oxygen is removed in a blast furnace by contact with carbon. Coke, a coal product, is the usual source of carbon. In this process, the iron becomes contaminated with some of the carbon. This extra carbon is in turn removed in the steel-making processes by using controlled amounts of oxygen. The resulting product is formed into various shapes by rolling or other processes. Steel may also be heat treated. Okay, other countries provide other necessary materials. We do have some of them here in the U.S. as well. Let's move on to breaking down the individual elements. Iron ore, so bulleted item. Iron ore is a metallic element that is the most abundant and most useful of all metals. It occurs in the free state only in limited quantities in basalts and in meteorites. So right there, something I want to take note of is, what did it say? Basalts, correct? What is the majority of our rock in Central Oregon and the Cascade Range here on the west coast made of? It's basalt rock, right? So, when I first moved here, I got a place. I'm not on city water, I'm just outside of the city. And my well house was getting a lot of sand and gravel in there. And I took it down to a local pump shop, and they run a magnet in there. And they said, "Oh, it's got to be flaking coming off the inside of your piping because it's all magnetic." And I thought to myself, well, now, isn't basalt rock magnetic? I didn't say anything because, again, they're the experts. But I went back and started researching this, and there is a ton of iron within basalt rock, which is also probably why it's so hard to break up and drill. Anybody around here, most everybody around here knows that. So we have a tremendous amount of iron. Usually anywhere there's some volcanic activity, there is. But that's something I just wanted to point out, okay? Let's go down to magnetite. Okay, here's the chemical makeup of it, Fe3O4. So ferrite, 3 parts ferrite, 4 parts oxygen, okay? It's a brownish ore that contains about 65 to 70% iron. Let's go down to hematite. Hematite is known as red iron, contains 70% iron. It's widely mined in the U.S. Limonite contains from 52 to 66% iron. Siderite contains 48%. Taconite is a low-grade ore that contains from 22 to 40% iron and a large amount of silica. It is green in color. Jasper is an iron-bearing rock. The ore is predominantly magnetic or hematite. Okay, we can break this down so much further into chemistry, so forth. However, we're not going to. We're just going to leave this right here. Okay? Is it important that you know exactly what percentage? No. It's just kind of something interesting to know that different rocks, different materials, and so forth have different percentages of iron within them. Okay, iron ore mining.